Right, good morning, everyone. Thank you for being on time. We will be starting lecture 2 today, which is about macromolecule. It's going to seem a little bit overwhelming at times because there are a lot of new information, but I will try to not go too fast, and I'll try to summarize things wherever it's appropriate. Okay, so just stay with me and try to ask questions if you're a little bit confused. Now, before we start the macromolecule lesson, though, we actually have to do a little bit of chemistry background information, just to make sure that we're all on the same page. I know you might have learned some of these things already in your chem class, but I need you to be at a certain level with the chemistry before you can understand some of the biology stuff that I'm teaching you. So that's why we have to do that. So I'm not sure why the pictures are not showing up. Let me try to reset this. Give me a second. Let's try that one more time. There we go. Okay, so starting with some basic chemistry concepts, you might have learned a little bit of this in chem class already. So there's going to be a little bit of overlap here. So what is matter? Matter is everything that takes up space, so it has a volume and it has mass associated with it. So if you think about just anything in this room, like the mouse here, right? It has weight on it. I can put it on a scale and it will register weight, and it takes up space. It has volume. So this is made up of matter. Right? We are made up of matter. Table is made up of matter. But something is not always so obvious. Like if you think about the air that we breathe, right, we can't really feel its weight too much because we're used to the pressure, okay? But it still has weight and it fills up the room, so it also has volume associated with it. So the air that we breathe, the air that's in this room, is also made up of matter. Now, matter can exist in different states. It could be solid, gas, or liquid. The most familiar example that we have would be water. Drinking water is in the liquid state. You can put it in the freezer and it turns into solid. Or you can heat it up and it becomes water vapor. And then it will be in a gas state. Right? So depending on how much energy you provide to the matter, it gets cycled between the different states. All the matter that we know of in the entire universe are made up of elements. Okay? Elements are substances that cannot be broken down further to create other substances. So let's say we take oxygen, for example. Oxygen is an element because we cannot break oxygen down into new things. Okay? Oxygen is the most basic substance that we can get without engaging it in some kind of reaction. However, if you take water, and I asked you this before, right? What's the chemical formula for water? Yeah, H2O, right? H2O is 2 parts hydrogen and 1 part oxygen. If you run an electric current through water, you can do this easily at home by dropping a battery into water in some cases, and it will then start to break down back into hydrogen and oxygen. Come on in. And so water is not an element because you can break it down further into other substances. Right? What makes up element? Well, the smallest unit you can have for an element is what we call an atom. These are basic building blocks for elements. So oxygen would have oxygen atoms. Carbon would have carbon atoms. Every single element is going to have its own unique atom that makes up the whole thing. Now, inside the atom, there are more things Did you guys learn the atom in chem class yet? Just wondering. Yeah. Okay. So you probably are familiar with the concept of protons, electrons, and neutrons, right? What I need you to know for bio is that protons are positively charged. P for proton, P for positive. Whereas electrons that are kind of whizzing around, they are negatively charged. Okay? No charge for the neutrons, though. Okay? So each atom is going to have a fixed number of protons, but the electrons and neutrons, they actually can change in different situations. Okay? But protons are fixed. All the oxygen atoms are going to have the same number of protons. All the carbon atoms are going to have the same number of protons. Okay? So how do you know if something is an element or not? Well, you can look at the periodic table. If it's on the periodic table, then it's an element. Right? Is nitrogen an element? Well, you can see nitrogen is right here. So that is indeed an element. Okay? You probably have a better periodic table from chemistry because they will list the names for you. Okay, this is just like an overview. It doesn't really matter. Is water an element? Well, there is no such thing as water on this periodic table. Right? Like you might think W is water, but it's not. If you look it up, it's tungsten. It's the stuff that's in your, like a light bulb, like the old school light bulb that we used to have. It's made up of tungsten. But water is not on it, so water is not an element. Right? Okay, so how do you know if it's element or not? You just check the table, basically. Right? If it's on the table, then that means you cannot break it down further. Then by definition, it is going to be an element. So many elements, right? Like 118 of them. Some of them are synthetic. They try to make it in the lab by smashing, nucleus together at very high speed. But these are the ones that we discover so far. But how many of them actually exist in the body? Well, you might be surprised. More than 96% of the body only consists of 5 elements. Of the entire periodic table, only 5 elements are used to make up more than 96% of the human body. And you would have to know what these are. Okay? Carbon. Carbon, we are carbon-based organism. And carbon is very good at making chemical bonds. It can make up to 4 bonds, as you will learn in chem class, with other atoms, making it a very good building block. Where do we find carbon in real life? Can anybody give me some examples? Where? Sorry? Sorry? Not quite. Carbon usually is not in a gas form, but good try. Morning. Anyone else? I mean, you're writing with it, right? A lot of you. I don't have one actually. A pencil, okay? The pencil that you're writing with, people call it lead, right? Okay? But that's actually not lead. Maybe at some point in the past it's lead, but as you might know, lead is actually very poisonous, right? So they changed it to graphite now, and graphite is carbon. Okay? Do you guys have an example of some very expensive carbon that you might have? Either wearing it or at home, or do you guys know what I'm talking about? No? Okay. Diamond, right? Diamond is carbon. Did you guys know that? Right? Diamond is pure carbon. Right? Graphite, I said. Right? Charcoal, all of them are pure carbon. Right? It's just the arrangement is a little bit different, right? So we have a lot of carbons in us. Nitrogen, 70% of the air that we breathe are nitrogen. We can't use them though. Okay, we breathe it in and then we breathe it out. Is as if we never in our body. Like we can't use it in its elemental form. Oxygen, 21% of the air that we breathe are oxygen. The numbers are not important. You don't have to write them down. How about hydrogen? Okay, what do people use hydrogen for? Like in the past, maybe. They don't use that anymore because it's dangerous for that purpose. No? Balloons, right? Okay. Do you know they can fill balloons with helium and then with hydrogen, and then what do the balloons do? They float, right? Okay, but because it's flammable, it's dangerous to have flammable stuff at kids' party, so now they use helium instead. Okay? Helium is not flammable. There is a famous accident. It's called a Hindenburg. It's like a Zeppelin, like a really big kind of like an air balloon ship thing. They filled it with hydrogen, and then the whole thing exploded and went into flame, okay, because hydrogen is so flammable. Okay, you can look that up. Phosphorus. Okay? Phosphorus is, people are not really familiar with it, and we actually don't have a lot of phosphorus, but it is one of the key elements that makes us up. You might find them in matches. Right? It helps create a flame when you strike the match. So these are the 5 basic elements that makes up over 96% of the human body. In addition to these elements, right, what about the rest of the 4%? It turns out there are some elements that we only need in small quantity, okay? And we call these trace elements. Right? Trace elements are elements that are only required in a minute amount, in a small amount. In fact, if you have too much of it, it's often going to cause some kind of problem for you. Not having enough is also going to be a problem. So I have some examples of trace element here. Zinc is needed for your immune system. Many people are familiar with calcium, which is going to strengthen your bone, but you also need it for muscle contraction. So having too much calcium is actually not good. You might think taking a lot of calcium is good for your bones, but if you take more than your daily recommended dose, those extra calcium might start to build up in your kidneys, and you might have kidney stones. Okay? Too much calcium in the blood will cause you to have twitching, right? It will cause uncontrolled muscle contraction. So it's all about having the right amount. Iodine is needed to make hormones that will help regulate your metabolism. Do you know which organ uses the iodine? There's only one organ in the entire body that uses iodine. The thyroid, that's right. Do you guys know where your thyroid is? Can you point to your thyroid for me? Yeah, very good. Okay, this is your thyroid, okay? It's the only organ that uses iodine. You also need magnesium for contraction. So you can buy all sorts of supplement from, Walmart, but generally it's good not to self-prescribe. It's better to, take it only under the advisement of your doctor. Okay, because like I said, overdose is going to cause quite a bit of problem for you. So here is a question you might see on the test. Which of the following is a trace element? So I might mix some of these things with these, and you have to pick it out. Okay. I have 2 conditions here that shows you what happened when there is a deficiency in some of these trace elements. Iodine deficiency can lead to goiter. Goiter is an enlargement of the thyroid gland. When you don't have enough iodine in your diet, the thyroid gland gets bigger, trying to compensate for a lack of iodine. Now, iodine deficiency is not the only cause for goiter. There are other reasons a person can have an enlarged thyroid. However, iodine deficiency related goiter is not a problem in North America. How do you get your iodine? Do you know? You probably don't think about it, but where do you get it from? Salt, that's right. The salt that we take, just table salt, in Canada, it's iodinized. They purposely add iodine to it so that we're not going to suffer from iodine deficiency, okay? Natural sources of iodine include shellfish, okay? If you eat a lot of seafood, for example, they tend to be rich in iodine. Calcium deficiency, I'm sure many of you have heard of osteoporosis, and that is when your bone weakens and there is not enough calcium deposit in it, and it becomes very porous. It's like Swiss cheese here. If a person with osteoporosis fall down, they might fracture a hip or something like that. Okay. Morning. Okay, so we were talking about atoms. So let's backtrack a little bit. Atoms of the same kind, they always have the same number of what? Is it proton, electron, or neutron, Jimmy? Proton, that's right. So all atoms of the same element, they are going to have the same number of protons, right? All carbons, for example, all carbons, they are going to have 6 protons. And you don't have to memorize these numbers. You will do it for your chem class. However, the number of neutrons might be different. Right? Some carbon, for example, if I have carbon 12, it would have 6 neutrons. Numbers are not important, okay? You don't have to memorize them. Carbon 13 has 6 protons, but 7 neutrons. Carbon 14, 6 protons, but 8 neutrons. So atoms of the same element that have different number of neutrons, we call them isotopes. Isotopes. Some isotopes are heavier than others. Carbon 14 is heavier than carbon 12, right? And 13 is heavier than 13. 13 is heavier than 12, okay? So the heavier isotopes sometimes tend to be unstable. And when it's unstable, it is going to break down naturally. Right? When some of these isotope breaks down, they give off a little bit of radiation. And often you can detect these radiation. Right? So by using isotopes, there are many different applications. For example, we can use carbon 14 to do carbon dating. If they dig up some kind of fossil, some kind of remain, and they want to know how old it is, they can check how much carbon 14 is left in it. And then they would know how old the skeleton is. Right? Iodine 131 is a radioactive isotope. It breaks down and it gives off radiation. What organ uses iodine again? Do you remember? The thyroid, right? So if someone has thyroid cancer, they will be given radioactive iodine. The radioactive iodine will only go to the thyroid because it's the only organ that uses it. And then it starts breaking down in the thyroid and give off radiation. The radiation will kill the tumor cells, in theory. If you have a smoke detector at home, and you should, because it's by law, there is a little bit of americium-241 in it, which is another kind of isotope. The radiation is needed for the smoke detector to work, but it's not harmful radiation. It's not something that's going to cause you to become ill. It's very, very weak. It's only confined within the smoke detector. So these are some examples of where we would be using isotopes. Okay, I'm not going to test you on these things, okay? But you should know what an isotope is. Same number of protons, but different number of... Excellent. Electrons can also be different. Right? Electrons can be exchanged between atoms. They can gain electrons, they can lose electrons. Electrons are negatively charged. So if something gains electron, then it becomes negative. Let me just close the door. On the other hand, if an atom loses electron or electrons, more than one, then it will become positive. For example, sodium. Does anybody know the symbol for sodium? Yeah, Na. When sodium loses an electron, it becomes Na plus. Okay. When chlorine gains an electron, it becomes Cl negative. Right? Other things would be like potassium can become potassium plus. So all these things that have gain or lose electrons, they become an ion. Right? An ion. And ions can be dissolved in your bloodstream and they form electrolytes. Electrolytes. So when you drink sport drinks after exercising, I mean, it's mostly water and sugar, but there are also electrolytes in it. Okay? And we need to maintain our electrolytes because we sweat them out. And when your body have very low electrolytes, it's very dangerous. It will shut down. One of the number one leading cause of death in developing countries or low-income countries for kids is actually diarrhea, because they don't have access to clean water. Okay. So when we have diarrhea, it's kind of like a nuisance. Okay. It's an inconvenience, but then we drink clean water, we replenish the fluid, and we are good. But for these kids, if they have diarrhea, they don't have a clean source to replenish their fluid and their electrolytes. Okay. And they basically die from dehydration and lack of electrolytes. Okay. So ions are very important in the body. Any questions so far? All right. Quick recap. Everything we know in the universe is made up of, yes, elements, which are made up of atoms, right? Okay. And atoms are the same for the same element, but they might be heavier or lighter because there are isotopes. Okay? And then they can form ions by gaining or losing electrons. Next, if you remember the hierarchy of organization, we can actually take atoms and combine them together in fixed ratio to form molecules. Right? So let's take water as an example again. All the water in the entire world is H2O. If someone tries to sell you H3O, don't buy it. It's not water. In fact, if you add an extra O, H2O2, does anybody know what that is? It usually comes in a brown bottle at the pharmacy. Peroxide, exactly. That's hydrogen peroxide. That's for cleaning your wound. You can't drink that. You're going to poison yourself, right? So just by adding an extra atom, it's going to change the molecule completely, okay? For those of you who missed it, this is hydrogen peroxide. Okay? Not important, just giving you an example, okay? Now, let's use another example. Over here, we have sodium. If we, figuratively speaking, if we zoomed in, we will be able to see the sodium atoms. Okay, so that's sodium atom. They all have 11 protons and 12 neutrons. Okay, some might have more neutrons than others, but they are all sodium atoms. Okay, they all behave in the same way. They all have the same properties. Okay? So sodium, for those of you who don't know, is actually a metal. Right? But when we think of metal, we think of something that's hard, something that's, really strong, right? But not for sodium. Sodium is actually very soft. You can actually cut it with just a butter knife, okay? And sodium is also very reactive with moisture. If you search it up on YouTube, maybe during the break or something, there are people who drop a chunk of sodium into a bucket of water, and spark and fire is going to go all over the place. Right? So that's why the guy's wearing a glove, you can see. Because the moisture on your skin can set off a reaction with the sodium. Okay? If you have sodium, you actually have to store it under oil to prevent it from, reacting with the moisture in the air. So really explosive stuff. You don't want to be, keeping it in your house. All right. Chlorine is very poisonous as well. Okay, it was used to create mustard gas during the World War. And if a person inhaled chlorine gas, it very rapidly destroys your lungs and you suffocate and die. Again, not something you want to keep in your kitchen. The chlorine is made up of chlorine atoms. Now, if you combine these two chemically, if you allow the sodium to react with the chlorine, okay, there's going to be a violent explosion, violent reaction. But in the end, you're going to get sodium chloride. Sodium chloride is just table salt. Okay, if you zoom into the sodium chloride, you would have individual sodium chloride molecules. Each molecule consists of 1 part sodium and 1 part chlorine. Okay, and these would be sodium chloride molecules. Salt, of course, as you know, is not explosive and is not poisonous, right? Okay, so when you create a molecule, the properties it has in the end is very different compared to the atoms that are used to create it. Okay, they tend to become more stable and has its own unique set of properties. Does that make any sense? So atoms can come together to form molecules, right? But atoms is like the very small level, right? On a bigger level, we can say elements can come together to form compounds. All right. Now here is a little bit of concept that people sometimes get confused, right? I keep on telling you sodium is very explosive and you know you don't really want to be handling it and so on and so forth. But you know earlier I was just telling you sodium is it's an important electrolyte, right? So how come it's you know we're not explosive ourselves and things like that, right? You got to understand this here is elemental sodium. This is the stuff that has not you know gain or lose electron. Right? It's in its elemental form. The ones that we need in our body, it's the ionized form, okay? It's the form where it has given off an electron and it's able to dissolve in water. Okay? Same thing, when we say we need calcium in our diet, we are not talking about elemental calcium. Elemental calcium, again, is very reactive with water. We're talking about the ionized form. Okay, so you got to make that distinction. When people take calcium supplement, that white pill, that whole pill is not calcium. Okay, it's in some kind of compound. It's in some kind of molecule state. So that's that. Next, we're going to talk about how we actually glue these atoms together. And what holds the atoms together in a molecule? Well, it turns out a bond, a chemical bond, is kind of like a type of glue. And there are two kinds of glue here. We have the stronger glue, which is called the ionic bond. So in an ionic bond, there is a transfer of electron, sometimes more than one. So sodium chloride is a good example. Sodium would be giving off an electron, and chlorine would be accepting it. Okay, for reasons I'm not going to go into, sodium doesn't like to have an extra electron, actually. And chlorine likes to have an extra electron. So this forms a perfect partnership. Okay, when they come together, it forms sodium chloride. Okay, so ionic bond, it's a transfer of electron, usually is stronger. On the other hand, we have something like water, and in water, what's holding the atoms together is the covalent bond. Covalent bond. And instead of a transfer of electron, there is a sharing of electron. And so they tend to be a little bit weaker compared to ionic. Next, let's talk about organic molecules. Organic, the word means different things when you use it in different contexts. People say they want to buy organic food. That means it's being grown without use of growth hormone or pesticide and stuff like that. But when we say organic molecule, we are just referring to molecules that has carbon in it. Okay? If something has carbon atoms, then it's organic. Many biologically important molecules are going to be organic. For example, glucose is an organic molecule. The formula for glucose is C6H12O6. You will eventually remember it because we will be talking about glucose quite a bit. Protein is an organic molecule. There's no chemical formula for protein because there are many different kinds of proteins, and it really depends on which one you're talking about. But it is an organic molecule. Right? Lipid is an organic molecule. Not all organic molecules are going to be in some kind of living things. Okay? There are many other different types of organic molecules that are used in everyday life. such as polyester. Where do you find polyester? Clothing, right? Exactly, right? In bags and whatnot, right? It forms the water-resistant type of material. Methane is another example of an organic molecule. It's CH4, and it's a greenhouse gas, right? So these are all organic, but not within a living organism. Okay? There are some exceptions to the rules, though. These molecules, they have carbon, but people who came up with the rules are like, we don't count them as organic molecule. Okay? Even though they have carbon, we don't consider them as organic molecule. Anybody know what CO is? How about this one? This one people know, right? CO2 maybe? Carbon dioxide, right? Because there are two oxygen and we are breathing out carbon dioxide with every breath. How about this one? There's only one oxygen, so it's carbon monoxide. That's right. Do we want carbon monoxide around us? No, carbon monoxide is poisonous, okay? But you can smell them, you can see them, you can taste them. That's why you need a detector, right, for carbon monoxide. CN is cyanide, which is also poisonous, okay? And we will learn about why cyanide is poisonous later on in the course. So there you have it, organic molecules. Let's talk about water briefly. And for that, I'm gonna do a note for you. Not a lot of note to copy today compared to last class. So water. And this is how people draw a water molecule, okay? It's like drawing Mickey Mouse, with the ears. So the ears are the hydrogen, and the phase is the oxygen. If you remember from earlier slides, is it ionic bond or covalent bond that's holding the atoms together in water? Covalent bond, very good, right? Covalent bond is a sharing of electrons, right? So H and O are sharing electrons. However, when we say we share something, the idea is like, we get to use it together, right? 50-50. Okay? But in reality, that's not always the case. Like my kids, I buy them a toy. I'm like, okay, please share. But then my older one is always like hogging it, okay, playing with it more of the time, right? And that's kind of the situation here with oxygen and hydrogen. Okay? Oxygen is like my older kid. It's hogging. The toy is hogging the electron. Even though they're sharing, but because of the property of oxygen atom, it pulls the electron towards itself. And as a result, the oxygen here is slightly negative. Okay. There's a symbol for slightly. It's like an 8, but you never finish it. So slightly negative. And then these are slightly positive. Okay, so even though they are sharing, it is an uneven sharing of electron. Oxygen is pulling the electron towards itself. Now, overall, the molecule is neutral. It didn't gain or lose any electron. The number of protons, electrons are equal in the water molecule, but it's the distribution of electron that's uneven. So for molecules that are behaving this way, we call them polar. Okay? Polar just means part of it is slightly positive and part of it is slightly negative. Now that creates an interesting situation for water. If you put water molecules next to each other, and they're always going to be next to each other. Okay, remember the ears are the hydrogen. The slightly positive hydrogen will be attracted to the slightly negative oxygen. Right? So they behave like tiny magnets that have an attraction for each other. Okay? And these little interaction, these attraction, we have a name for them. It's called a hydrogen bond. And they exist between water molecule. So hydrogen bonds between water molecule allow them to stick to each other. That is why you can suck water through a straw. And when you drink water through a straw, the water molecule pulls the next one up and the next one up and the next one up. So it forms a chain that allows it to go up the entire straw. Here is another thought experiment that we can do. Let's say we have like a dime. Okay? We don't have pennies anymore, sadly. So let's say we have a dime and you have an eyedropper. And then you're going to be dropping water on it. Just visualize this in your head, okay? How many drops do you think you can fit on a dime? It's like, throw me some numbers.
2.
2 drops, okay. Anyone else? Like think of a dime, a really small eyedropper, and you drop the water slowly. How many drops do you think you can fit on the dime? Anybody go higher than 2? 3? Huh? Very cautiously increase by 1. Right. You can actually do it, if you do it slowly, you can actually fit like 10 or 15 drops, okay? And you might be surprised, but not really. If once I draw it for you, you will be like, oh, okay, I see it, right? Like if you drop it slowly, the water actually forms a dome, right? Okay. And that's because water has the hydrogen bond. It's able to hold on to each other so it doesn't spill over. Okay. One way to visualize this is, if I ask, 5, 6 of you to try to stand on the table, right? Or 10 of you to stand on the table, eventually to prevent people from falling over, you're gonna have to grab onto them, right? Okay, that's what the water molecule is doing. They are grabbing onto each other. Right? This ability to cling on to each other creates what we call surface tension. Surface tension. So surface tension, as a result of the hydrogen bond, prevents the water from spilling. And of course, eventually it will spill. Right? It can only do so much, right? That's why some bugs can walk on water, right? It's because of the surface tension. Forms a film. Are we okay? Hopefully. Okay, now I do have some news for you. Let me just pull up the schedule for you guys. I mean, not everybody is here, but that's okay. I'll tell you anyways. I'll post an announcement. The schedule, you guys at 2:03? So our first quiz is supposed to be when? 18th, right? 18th is next Wednesday, okay, a week from now. But judging from the pace we're going at, I won't be able to. We won't be able to finish everything. I won't be able to teach you everything that's on quiz 1 by today. Okay. So I don't want to be teaching you something next Monday and then quizzing you on it on Wednesday immediately. All right. So I am going to postpone the quiz to the 23rd. Okay. So please write that down. Now I will today I will post a review video for you to watch. Okay, for the quiz. Don't wait until the 22nd to watch it. Okay, start watching the review video. The review video tells you exactly what you need to know for the quiz. Okay, no tricks. Okay, for sure. You study from the review video, then you should be able to do quite well. All right. If you know everything from the video, then work on the study guide. That will help you, do even better. Okay. So check the news section after class, and you will see the link to the video. Rachel, you had a question? Okay, sure. Yeah. All right. Water is also an excellent solvent. Solvent are what we use to dissolve things in. All right, it's usually liquid. So if you think of a pack of these, Kool-Aid powder, the powder is the solute, and the liquid, water in this case, is a solvent. And when we mix them together, we get a solution. So anytime you dissolve something in water, you get a solution. So can you give me some examples of substances that can dissolve in water? Sugar, good. Salt, yeah. What's that?
Pre-workout drink.
Oh, drink. Okay, yeah, like is that like a brand? It's a powder. Okay, that you put in. Yeah, sure, right. Yeah. So all these things that can dissolve in water, we call them hydrophilic molecules. Hydrophilic. Hydro is water. Philic is loving. Okay, so these are water-loving molecules. Generally speaking, if something is polar or ionic, such as salt, they can be dissolved in water. Because water itself is polar. There's a phrase that they use in chemistry, like dissolves like. If they are both polar, then they would go into each other with no problem. Okay. So sodium chloride, NaCl, is hydrophilic. It can dissolve in water. Other example people were saying would be like sugar, I heard, right? There are these like pre-workout drinks you were saying. Anything else? Like, can you give me another liquid that would mix well with water? Just something in the kitchen, okay? Nothing fancy. Don't give me things that I cannot spell. Yeah. Yes, that's exactly what I was thinking. Thank you. I feel very good when people have the exact same answer I was looking for. Vinegar, right? Now give me something that cannot dissolve in water. Oil, right? Oil, water don't mix, right? So oil is hydrophobic. Hydrophobic. Phobic means afraid of. Right, so these are molecules that are afraid of water. They don't mix well together. So things that are non-polar, they tend to be hydrophobic. Now, just to refresh your memory, what makes something polar is the uneven sharing of electron, right? For non-polar substance, they have even sharing of electron. It's 50-50. There's no hogging of electrons. Okay, so if they are share evenly, there's no slightly positive, so no slightly negative, and that makes it non-polar. And when it's non-polar, it's hydrophobic. And you need to know these terms because it's important when we talk about the macromolecules. Hydrophilic, hydrophobic. Now, I always meant to include a clip to show the class. but then I always forget, never get around doing it. And then I always remember when I get to this slide. There is this YouTube video I saw. It's this product. I don't know if you can actually buy it or if it's still in experimental phase, but it's a spray that you can purchase to spray on your shoes. And once you spray on your shoes, it has a hydrophobic coating on it. So if you buy like a brand new, white running shoes, you spray it with these things, you can literally run through the muddy water and it will not get dirty. Because muddy water is water, right? With the hydrophobic protection, it doesn't allow the mud to cling onto it. Okay. There was also a guy who sprayed it on his hand, and then he stick it in the water, and you can see in the video that the water doesn't cling on the hand. There's almost like a bubble layer around it because of the hydrophobic repulsion. Okay. So check that out. It's quite interesting. Maybe I'll remember to put it in next year. Okay, lastly, we have the pH scale. Right? Do you guys know what the pH scale is? What does it measure? Yeah, acidity, right? Opposite of acidity. The opposite of something that's acidic is basic. Right? Acidic and basic. So things that are acidic are generally things that we think of as like sour. Right? So vinegar is acidic. Do you know you have acid in your stomach? And that's hydrochloric acid. That's acidic. So generally, these are things that are less than 7 in the pH scale. Base is more than 7, greater than 7. So these tends to be bitter stuff. Okay? Slippery when you touch them. You shouldn't really be touching very strong base without protection anyways. If you touch like bleach, bleach is very slippery, but if you keep rubbing, it actually burns your skin off, right? Okay. So they are corrosive as well. Right? That tends to be cleaning products. Baking soda is a base. And right in the middle, the pH is 7 for neutral things. Pure water is neutral. Right? Not the tap water. Right? If you let water sit in the room for a while, the pH actually changes because it sucks up the carbon dioxide from the air. Okay, but pure water is 7. The pH of our blood is very important. Right? For it to be compatible with life, our blood pH has to be within a very narrow range of 7.35 to 7.45. Right? So there are many different ways in our body to help us maintain this homeostasis. We learned that word last week, right? This internal balance. Having too much acid in the body is called acidosis. Having too much base is called alkalosis. You don't have to worry about this slide. I'm not going to test you on it, okay? You can keep copying, though. So acidosis and alkalosis can both be fatal, right? But we don't usually die from drinking orange juice, right? When we drink orange juice, our blood pH actually might drop, but that's okay because our respiratory system and urinary system will help undo that change, okay? It will bring it back up so that it's within the survivable range. Right? In addition, you have these things called buffers in the blood that helps you mop up extra acid, right, and extra base when they exist, and it keeps it inside a survivable range. Okay, so we'll talk more about pH later in the course, and definitely a lot more when we learn about the urinary system and respiratory system next year. Okay, so that was a lot of chemistry. I think we're done now. But before we go and do the bio, let's do a question here. Okay. What do you think? Yes, that's right. What was that again? Try again. That's good, Josh. Hi. Biology. No, not this. Yeah. Not quite. That's good. Try again. Yes, Angela. Anyone else? Yeah, good. Good. So the answer is water molecule is polar because it has uneven distribution of electron. That's what makes it polar, right? The oxygen is hogging it, making it slightly negative compared to the hydrogen. All right. I know I say this every class, but I just want to remind you to study these concept track questions as well. Okay? Sometimes they will be on the quiz. Not all of them, okay, but some of them. Like that one I promised you to be on, right? Okay, that's it for the chemistry. Let's go back to bio. Now we're going to be talking about the macromolecules. But before we go into the individual macromolecules, I'm going to teach you a little bit about like a theme that can be applied to all these macromolecules. First of all, there are 4 kinds of macromolecules that are important in a biological system in the body. Okay? We have carbohydrates, which people call carbs sometimes. Where do you get your carbs? If you had breakfast this morning, I bet you had some carbs, okay? What are some sources of carbs, carbohydrates in our diet?
Bread.
Bread, good. I had some bread too. Rice, yeah. Anything else? What was it? Sorry, I heard something, but potato, yes. Okay, so a lot of these staple food is very high in carbs, right? Okay, you guys are very good. You gave me the healthy ones. What are some like unhealthy sources of carbs? What's that? Pizza. Okay, yeah, the dough would have carbs, right? Okay.
Cake.
Cake, right? Sugary stuff has a lot of carbs in it as well. Okay, if you're craving for a granola bar or like a sundae or something that has a lot of carbs in it. Okay, proteins you can get from meat. If you're vegan, vegetarian, you can get it from beans, for example, right? Tofu, soy product, they are very good in protein for vegetarian and vegan diet. Lipids is basically fat. There are good fats and there are bad fats. We can talk about that. Let's just try it out. What are some examples of good fat that you can get? Yeah.
Ghee.
Okay, yeah, give. Anyone else? Avocado oil is very good, right? Okay, what about bad fat? What you guys put on your bread this morning?
Butter.
Yeah, butter, right? Butter.
Margarine.
Oh, margarine. Yeah, margarine is worse than butter, okay? But butter is not good either. I mean, it's tasty, but then too much of it is not good either, right? So these are not as healthy lipids. Nucleic acid, anything that's living would have nucleic acid in it. So if your diet has anything that's living in it, and it has to be, okay? Like whether you are vegetarian, vegan, or normal diet, everything has to have some kind of living things in it, okay? Plants are also living, right? Okay, not just animals. So that there will be nucleic acid. All right. So you can think of macromolecules as a polymer. Polymer basically means a long chain of repeating units. Okay. With the exception of lipids, these 3 things are polymers. They are very, very long chains of the same unit repeating itself. Okay, the same building blocks repeating itself. These building blocks, we call them monomers. Different polymer require different building blocks. Each kind of macromolecules has their own monomers. And we will be learning about them as we go. No need to worry about this chart at this moment. It's just an overview. Some people find it helpful to visualize macromolecules as a train. Right? So if you think about a go train, it's very long, but it's predictable, right? It's the same go-kart for each section, right? But if we're building a different train, if we're building like the TTC subway, again, it's very long, but the cart that we use would be different, right? Same thing for those CN rail train, it would also be different. Okay. Sometimes there are subtle differences between the cart within the same type of train. Right? And that's what we will see when we look into the different polymers. Okay. Now, this next part is a little bit heavy, but pay extra attention because there will be a quiz question on this, guaranteed. How do we get from monomers to polymers? How do we link them together? Okay? Don't worry too much about what the meaning of the hexagon is at this moment. Right? A few slides later, it will make sense. Right? If I tell you what it is now, it's just like too confusing, right? So there is a molecule right here that has a hexagon on it. Right? This over here, that's one monomer. That's one building block. And then over here, that's another building block, another monomer. And never mind what the hexagon is. What's important to see is that they both have OH on them, oxygen and hydrogen. Right? So it turns out when you want to connect these things together, you need to do a chemical reaction. You need to create a bond to hold them together. Remember, there are two types of bonds that we learned about: ionic and covalent. Right? So all the bonds that we will be talking about for macromolecules, they are all covalent bonds. Right? So how do you form that bond? How do you form that covalent bond? How do you share the electron? It turns out it's all the same. What you're going to do is you will be, like your body will be, removing a hydrogen from one and removing an OH from the other. And after doing that, you will be able to form a covalent bond that connects them together. So what happens to the hydrogen and the OH that came out? Well, H and OH actually makes water. So in order to connect them together, you have to remove a water molecule from them. Okay? And we call this dehydration synthesis. Right? Synthesis is to create. How do you create the bond? By dehydrating it, by removing a water molecule. Another word for removing water is condensation. Right? If you have condensation on the window, it's like the moisture is coming out, right, from the air. Now let's express this in another way. I know it can be a lot. Now do a big diagram for this one, okay? Because we're going to be adding some more information to it. So we can have these building blocks. What's the name we use for building blocks? Monomers. And we can connect them together. 1, 2, 3, 4, 5, 6, 7, 8. We can connect these guys together. And it forms a long chain. On the slide, I only show you how to connect two of them, but you can repeat the process. Now you can join them up and form a long chain. So the long chain is called what? If this is monomer, this would be a polymer. Very good. With the exception of lipids, all three of the macromolecules, they are polymers. In order to connect them, though, we have to do a chemical reaction. And the name of the chemical reaction is called dehydration synthesis. And another name is condensation reaction. You can use either one on the test. It doesn't really matter. I'm just showing you in case you see them online and then you're like, you know, this is different from what I've learned. What's going on? And what does that actually mean? Well, it means you have to remove what? What are we removing to connect them together? Hydrogen from one and OH from the other, and you get what? H2O, that's right. Remove water. So every time you connect them together, you are going to have to remove a water molecule. Okay? All right. Let's do a question here, and then we'll take a break. Now, let's say I have 4 monomers, okay? And I want to connect them together. How many water molecules will be removed in this reaction? Show me the finger. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. How many water molecules do we need to remove to connect these 4 monomers together? Good. Try again. Good. Too many. Try again. Try again. Try again. Not quite. Okay, I'm glad we're having this conversation, right? You know, if this is the first time you see this question on the test, you might not get it right. All right. So look. It's not that difficult. Okay, just watch. If I need to join this and this, I need one bond, right? Each bond requires removing 1 water molecule. So that's 1 water molecule. And then 2 water molecules, 3 water molecules. You understand? Every time you glue them together, every time you form a bond, you need to take out 1 water molecule. Okay? What if I need to connect 8 of them together? Then how many water molecules do we need to remove? 7, right? It's always 1 less, right? Right? Does everybody understand this? Yeah? Okay, let's draw it out. 1, 2, 3, 4, 5, 6, 7, 8, right? So how many bonds we have? 1, 2, 3, 4, 5, 6, 7. Okay. Each bond requires 1 water to come out. Okay. All right, break time. Let's take 5 and then we're gonna come back. Yeah, hold on, let me pause the recording first. All right, let's keep going. Now, if you are able to build them, you should be able to break them as well. So building it requires you to remove a water molecule. Then breaking it would require you to add a water molecule. Okay, to add a water molecule. So in this reaction, we will take the two things that are connected together. We will add a water molecule and we will break them apart. So hydro is water. Lysis is to break. Sometimes it's good idea to remember some of these prefix and suffix because they will be used in many different contexts. So hydrolysis is to break using water. So if I have this molecule here with 4 subunits and I want to break it all down, I would need to add 3 water molecules. I need to add 3 water molecules. Now back to our class notes here. All right. To go from polymers to monomer, it would be, as I said, hydrolysis. Hydrolysis. And hydrolysis requires you to add H2O. So this is basically what happens in the body. You eat your food, your carbs, your proteins, and whatnot. When it goes into your body, it's in the form of a polymer. Your digestive system adds water to it and break it back down into these building blocks. You can either absorb the building blocks as nutrients, as fuel, or you can use them to build things that you need in the body. Your muscle is made up of proteins, for example. So you can use the proteins that you eat from a diet, break it back down into building blocks, and then use them to build muscle. Okay, so basically, that's the theme that we're going to be exploring as we move forward. Okay, let's try a question together. This is going to be important. This is going to be on your quiz, okay? This specific type of question is going to be on your quiz. So never mind what the square is, okay? But let's say this square has an OH. And then I have another one here. Let's say I have a pentagon that also has an OH on it. And I want to connect them together to form a bond. Can you draw me the result? If you put them together, what would the result look like? And you can look at the PowerPoint to help you see what happens, okay? Let me put the question back on. Do you guys have it? Yeah? Okay. So you're gonna take an H from one and an OH from the other. It doesn't really which one you take the H from and which one you take the OH from. Okay. So you take the H here, you take the OH here. And when they come out, what molecule does it become? Water, right? And then I'm gonna basically draw it. I'm gonna have the square. I'm gonna have the O. This O is this O, right? I'm gonna draw it in red so you know. This O is this O. And then it's going to connect to the pentagon, right? You guys got that? Okay. How many marks do you think this question will be? Oh, I'm more generous than that. 2 marks. Yeah. Okay, you try now. The one on the quiz is not multiple choice, okay? The one on the quiz you actually have to draw. All right, just so you know. But yeah, let's do a multiple choice question. What do you think the answer is? Let me know. Good try. Yes, yes, yes. Yes. Yeah. Try again. Good. Good. Yes. Anyone else? Try again. Good. Good. What is it? Good. I think most people got it. Hexagon and pentagon. So you are looking for something that has one of each, right? Definitely not that. Definitely not that, right? So it's either this one or this one. But don't forget, after you take the H from one and the OH from the other, there's still an O that connects them together, right? That's why it is. Got it? Okay, I still haven't tell you what the pentagon and the hexagon represent, but here we go. Again, don't feel overwhelmed. Just watch the review video. I promise you it's going to be all right. Okay, just study from that, please. Okay? I'm not trying to fail you. Okay? If I fail you, it looks bad on me. I have to explain to my boss why so many people fail. Okay, you think I like that? So let's start with the carbohydrates. Okay. For each of the macromolecules, I need you to pay attention to what elements is it consists of. I need you to pay attention to the building blocks, biological function, and food source. Let me write down for you over here. Elements, monomer. Sometimes there's more than one monomers. And then function.
Biological.
Yeah, biological functions. And food source. Right, so pay attention to these 4 things. In fact, I encourage you to create a table when you have time later on to organize these macromolecules so that you can have them side by side. Like carbohydrates here, the elements are C, H, and O. Okay? Monomers, and so on and so forth. I'll tell you as we go on. So remember the 5 elements that makes up over 96% of your body? C, H, O, and then NP, right? Nitrogen and phosphorus, right? Okay. So of the 5, carbohydrates consist of C, H, and O only. Okay. Carbon, hydrogen, and oxygen. The word carbohydrate means it contains carbon and it contains hydrates, which is water. In fact, all carbohydrates are 1 part carbon and 1 part water. That's why it has a general formula like this. Now, you don't have to memorize a general formula, but let me show you an example of how this works. Let's say I choose a number for n. N has to be a whole number, okay? So let's say we choose 6. Then the formula is C6H12, because 2 times 6 is 12, and then O6. By now, do you recognize what this molecule is? I've seen it a couple of times now. Glucose, exactly. Glucose. Now, glucose is the main fuel of the body, but most people are not familiar with glucose because we don't have it in our kitchen. Okay, it's not something we can buy. Actually, it's really hard to buy glucose. You go to a regular store, there's not something called glucose that you can buy. Right? You can buy them though. It's a little liquidy thing, but we don't really use it in that specific form in terms of consumption. So what do we use carbohydrates for? Primarily, carbohydrates are used for quick, short-term energy supply. Okay? Many things that we do in the body requires energy, like writing requires energy, beating of the heart, breathing, all those activities require energy. How do we create those energy? Well, in our cells, trillions of our cells are constantly burning glucose, burning carbohydrates to provide that energy for us. Okay? We can burn proteins and lipids as well, but that's not the preferred source of energy. Okay? Our body prefers carbohydrates, prefers glucose specifically. In other organisms, carbohydrates are important for structural components. Take plants, for example. Plants have fibers in them, and those fibers are actually made up of carbohydrates. And we'll talk more about that in a bit. Shells of an animal, of seashells. So seashells of like mussels or crustaceans like crabs and lobsters, and even bugs, their exoskeleton, like the hard part on the outside, that's actually made up of carbohydrates as well. I don't know about turtle shells. I don't think turtle is actually made of carbohydrates, but definitely the seafood ones, okay? Okay. So for us, you and I, we do not have carbohydrates for structures, okay? None of the body parts we have are made up of carbohydrates in terms of structural support. But we do use carbohydrates for energy source. Okay. Now, this equation here, it's something that will go into a lot of details later on. You don't have to memorize it now, but eventually you will have to. This is called cellular respiration. Is the main reaction for energy production. Okay. It's 24/7. Even when you're sleeping, your cell will continue to burn glucose, reacts it with the oxygen that we breathe, and then it produces carbon dioxide and water as a byproduct. But more importantly, after this reaction, it creates energy. Plus energy. And we can use the energy for all sorts of stuff. As you will learn later on in chemistry class, this is actually a combustion reaction. We can substitute the fuel with different things. So instead of using glucose, you can change it to say octane. And that's basically what's happening in your car. Unless you drive EV, then that's different. But if you drive like a regular gasoline car, the gasoline is octane and it will burn with oxygen, produce carbon dioxide, water, and then energy to move the car, right? If you have a barbecue, what kind of gas do you use to fill up the barbecue tank? You guys know? Propane, exactly, right? So propane plus oxygen produce carbon dioxide, water, and then energy to heat your food. If you have a lighter, that's butane in it, right? So different fuels can be used to burn and create energy. But we, as humans, our cells prefers to burn glucose. And where do you get the glucose? From your food. Okay. We don't eat glucose as is in that form, but as you will see, the food we eat can be broken down by hydrolysis to create the glucose. Remember, when we eat the food, it's in the form of the polymer, right? Okay. So once it goes into our body, we can chop it off by adding water, and then we will get the glucose individually. Sources of carbohydrates. There are no shortage of carbohydrates in most people's diet, right? We can get it from starch. Some people mentioned potato already. Rice is rich in starch. Corn, wheat, pasta, cassava, yam, what have you. All these are very starchy things, and they are rich in carbohydrates. You can also get carbohydrates in the form of fructose. As the name implies, fructose are naturally occurring sugar that are found in fruits. Okay. Artificially, you will find them in corn syrup. Okay? So there is a lot of pushback nowadays of avoiding food that has high fructose corn syrup, because it's highly processed and it's not as healthy. Lactose you will find in dairy product, including milk. What do we call people who cannot consume dairy product? Lactose intolerant, right? Okay, so we'll take a look at why that is the case later. Sucrose, that's the stuff you have in your kitchen. Okay? When you buy sugar for baking to add to your food or whatever, that is sucrose. Okay? And of course, you will find a lot of sucrose in candy bars. If you read the ingredients of the candy bar, granola bars, I can guarantee you there will be sucrose in it. Okay, now we're going to talk about the monomers. Okay? Stay with me, guys. The monomers. The monomers of carbohydrates, there are different types, but there are three that I want you to remember specifically. Glucose, we already know, fructose, and galactose. Okay? Glucose, fructose, galactose. These are single sugar. That's what mono means. Mono is single, like a monorail has a one track, right? Saccharide is sugar. So these building blocks for carbohydrates are monosaccharide, single sugar. if you draw out the chemical structure, they look like these. And so glucose has a hexagon. That's what the hexagon was. Okay. Instead of drawing all these complicated stuff, some people just use a hexagon to represent it. It's easier visually, right? Fructose is a pentagon. Galactose is another hexagon. You are not responsible for drawing any of these on the test or quiz. Okay. I will also not show you a picture and ask you to identify it. Okay. You just have to memorize the names. That's all. Okay. So the pictures are here just to show you, what the hexagon and the pentagon represent. Understand? Okay. Monosaccharide, single sugar. So they are single and they are ready to mingle. We can take the glucose and the fructose, both of which are single sugar, monosaccharide, and they could join together. They could partner up by forming a bond. All right, you can see you can take an H here and an OH, and of course you get the water in the end. But more importantly, you are able to connect them together. You can connect the hexagon and the pentagon together to form a bond, and you end up having sucrose. Where do we find sucrose again? Do you remember? Yeah, but like when we say sugar, actually sugar is like an umbrella term, right? Like fructose is a kind of sugar, right? Okay. Sucrose specifically is what kind of sugar? Sure, yeah, candy, like kitchen sugar, right? Okay, the ones you have in your cabinet, right? So when you consume candy, when you consume sucrose, your body will break it down back into glucose and fructose by hydrolysis, by adding water molecule. Then you can burn the glucose, right? That's why, like, when you have some candy, usually it gives you almost instant lift in the mood, and you feel a bit of a good energy, right? Almost. It's because it's so easy to break it down, right? Immediately, your body can convert into glucose, and you can burn it, right? But that's not necessarily a good thing. Right? If you suffer from diabetes, you don't want the glucose to be elevated in your bloodstream because you cannot, control it adequately, right? So for people who have diabetes, they usually should cut down on these simple sugars. They should have more complex carbohydrates in their diet, right? So that they don't cause the blood sugar to go up too quickly. Right? So if you have quinoa in your diet, right, or if you eat like brown rice, right, those tends to be more complex carbohydrate. It takes a longer time to convert into individual glucose. Okay, so these things, once you connect them together, you have double sugar now. So we call them disaccharide. Okay. Monosaccharide, disaccharide. So here are the three common disaccharides I want you to remember. Right? They all have a glucose in it, at least one glucose in it. But depending on which one you combine it with, you're going to end up having different things. Right? So just to reiterate, all these things are monosaccharide. And these ones over here, these ones, what do we call these ones? Disaccharide. So glucose plus glucose gives you maltose. You will find maltose again in most candy bars. You will also find maltose in alcoholic beverage. Okay. Next one is easy to remember. Again, they all have one glucose. Glucose plus galactose gives you lactose. Right? The word lactose is in both here and here, right? Where do we find lactose again? Yeah, milk, dairy products. Glucose plus fructose gives you sucrose, which is the kitchen sugar. So a couple ways I can test you on this. I can mix them all up and ask you which of the following is an example of monosaccharide. Then you have to be able to choose them. I can ask you, when I combine glucose with galactose chemically, what is the end result? And then you have to be able to choose them. So a quick word on lactose intolerance. When we consume a product that contains lactose, we are supposed to break it back down into glucose and galactose. But all reactions in the body needs something called an enzyme to do it. Okay, we'll learn more about the enzyme later, okay? But each reaction requires an enzyme, right? But some people don't make that enzyme. Right? The enzyme that you need is lactase. And so if you don't have that enzyme, you cannot break down the lactose, and the bacteria is feasting on it instead. And so all those extra bacterial activity gives you the symptoms of lactose intolerant, gas production, bloating, diarrhea, and so on and so forth. But fear not, you can buy this product and just basically take the enzyme as a pill form. You eat those pills first. Now you have the enzyme in the body, and you can go enjoy your Sunday and whatnot. Okay. So we went from monosaccharides to disaccharides. And then the ultimate level, the highest level, is polysaccharides. Let's not forget, carbohydrates are polymers. So they are not just going to be like two red circles together, right? They're not just going to be two subunits. It's very, very long, like a train, right? So polysaccharides has as many as 100 or 1,000 of these units connected together. To keep things simple, we are only going to be looking at 4 types of polysaccharides. There are 3 here. First, cellulose, glycogen, and starch. They are all made up of glucose. They are nothing more than a bunch of glucose connected end to end with each other. Okay, so glucose keeps on going for hundreds and thousands of times. Sometimes they are branched, other times they are not. So depending on how much branching exists, it's going to be one form versus the other. Okay, so let me go through these with you and tell you what the functions are. Let's start with cellulose. Cellulose is not a branch. It's just glucose after glucose after glucose. Each of these hexagons represent a glucose. So this is one strand of cellulose. This is another strand, and another strand. And for reasons we're not going to go into, cellulose are very strong because you can take these strands and you can braid them together, and it becomes almost like a rope. And so it gives them very strong properties. And we would find cellulose in plant cell wall. Plant fibers, okay, the plant fibers. Now, cell looks like this, right? They are the building blocks for living things. Okay. All living things are made of cells. We learned that already. But for plant cells specifically, they have a cell wall around them. Okay, so this is a cell wall. We don't have cell wall. Only plants do. And yeah, it's outside of the membrane. And it's made up of cellulose. Okay? It's really strong. So that's the fiber that's in the plant. When we eat vegetables, we are consuming these fibers. We cannot break down the fibers, though. We cannot break down the cellulose because we don't have the enzyme for it. But dietary fiber is good for our body because it helps move things along in the intestinal tract. Do you guys ever see that commercial with it's called Metamucin? Is this powder that people can drink? And yeah, and you see these happy actors sliding down the slides, right? After taking the product. Right? That's basically what it does. Okay, the slide is like your intestinal tract, and the cellulose in the product helps you move things along. Right? If things don't move, then you get constipated, right? And we know that's not fun. So cellulose, it's for the fibers in the plant, very hard to digest, even for animals that graze on them, including cows. Did you know cows have multiple stomachs? Yeah. So if you observe a cow, they actually chew all day long. They chew on the grass, they swallow it, and then they have special bacteria in their guts to help them digest the cellulose. But even so, it's difficult to break down. So every now and then they would burp the partially digested grass back up, and then they would chew some more, and then they would swallow it. And they do this a couple times throughout the day. Every time they burp it back out, and this is true, they actually burp out a lot of carbon dioxide as well. So cow farms are actually one of the main contributor to greenhouse gas, right? Because of all the burping from the cows. Right? So they're actually training the cows to burp in these special devices now so that they could capture the carbon dioxide from them. That's why they say, right, eating beef is not good for the environment. Right? If you need to eat meat, they say chicken is better because chicken don't have these kind of greenhouse gas emission. Anyways, that's just a side fun fact. Moving on, starch is another example of polysaccharide. Starch looks like this. It has a main branch. It's like, glucose, 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 so on and so forth. But every now and then you would have a branch. The branch is also glucose. Okay, glucose, glucose, glucose. And it branches out like that. Okay. So starch is the storage form of energy in plants. Plants, they have to make food for themselves by doing photosynthesis, staying in the sun. And they store all these extra food in the stem or in the roots. They're supposed to use it for themselves in the winters when there are less sunlight. But of course, we can harvest the root and the stem and we can eat it for our energy source, right? So potato, it has a lot of starch, and starch is an example of polysaccharide. How about you and I? Where do we store the extra? Well, we store them in the form of glycogen. So glycogen, as you can see, is even more complicated. It has a main branch, and then it has other branch coming out. And on the branch, there are even more branches. Okay, so it's very complicated molecule. And we store glycogen in the muscle and the liver. If you did not eat breakfast this morning, you are running on your glycogen reserve. Okay? When your blood glucose level is low, your liver automatically cut off the glucose from the brain. Like there's a glucose, so chop it off with hydrolysis, and then you can burn it. And you chop another off, and then you will burn it. And that's what's fueling you if you're fasting right now. Okay? So this summarizes the three kinds of polysaccharides. We have the starch in the potato. We have the glycogen in the muscle. That's what they look like under high power microscope. And then we have the cellulose in the plant leaves. Just one more, and then I'm gonna stop. The last kind of polysaccharide is this thing called chitin. Chitin. Chitin is made up of glucose with a little bit of modification. So these kind of glucose has a nitrogen group in it. You don't have to memorize it, okay? And the chitin is what makes up the shells of crustaceans, right? The lobster, the crabs, the seashells, okay? They have chitin. And chitin actually is useful for us because when you use chitin as surgical threads, they are biodegradable. So let's say you remove your wisdom teeth and they stitch you up with chitin, the stitches would just melt in your mouth after a while. And so you don't have to go back to remove the stitches. And that's better for wound healing, right? So someone asked me yesterday, like, what if you're allergic to shellfish and then they stitch you up with the chitin or something, right? The chitins are made in the lab, right? It's completely synthetic. There's no connection with the actual wild life form, right? So, you wouldn't be allergic to it in that regard. Okay, let's do 2 questions, and then I'm gonna do a quick summary for you, and then we'll go home. You still have another class, right? But you know, I guess you can't go home yet. What is the answer to this one? See if we can do it without looking at the slide. Good. Good try. What is it, Josh? See a quick flash. Nope, not that one. Good. Good. Yes, Cindy. Try again, Christine. Good. Good try. Yeah. So this is like a factual thing, right? You just have to memorize it, and you should be able to get the answer, right? Sucrose is glucose plus fructose. Okay. Okay, this one is a little bit harder. You won't see multiple choice question with multiple correct answers on quizzes, okay? Only for the online one that you take, which is quiz 2, okay? But for the in-person one, there will always only be just one answer. Okay? But we're just practicing here, okay? There are more than one correct answer here. You can show me both, like, you know, 1 and 2 or something, okay? Go ahead. That's one of them, yeah. Good. That's one of them. Yes, we're looking for the false one. Yeah, that one's not. That's one of them. Yes, that's one of them. Yeah. Good. Good. Okay, all of you only gave me one of the answers. There are more than one correct answers here, right? So what's the other false statement? Not quite. Good. No and no. No. Okay, let's take them up. We are selecting all the false statement, all the incorrect statements, right? Okay. So let's take a look at the first one. Polysaccharides are important both for energy storage and provide structure to cells. That's true. Energy storage would be starch and what else? What do we use to store in the liver? Glycogen, that's right, okay? And structure support would be like cellulose, right? So that is correct. Next one. Glycogen is important both for energy storage and to provide structure for cells. That's not true. Glycogen does not provide structure for cells. Cellulose is only found in animals. Do we have cellulose? No. What does? Plants, okay? So not animals. That's why this is also false. Glucose, fructose, galactose are examples of monosaccharides. That's correct. Starch is a storage form of polysaccharide made by plant cells. That's also correct. Okay, so 2, B and C are incorrect. All right. We still have 5 minutes, so I'm gonna keep you. Let's take a look at this here. Okay, study guide, you should be working on them, but I want to take this up with you before you go. Okay, because I know like it's too much information and I know you are not able to retain it. With one explanation, it's hard to retain all of it. So let's just quickly do this and then I will let you go. Okay, if you have your study guide, you can follow along. Otherwise, we will you can copy this later. Okay, so number 9, use the diagram below, show how a bond is formed between 2 glucose molecules. I probably won't ask you this on the test, but you know, it's good to have an idea. I mean, like there's so many OHs and H, right? Like how would you know which one to remove, right? So it's not a fair question. You have to know a lot of chemistry to know that. But I just want to show you to help you remember it. So for example, we have an H here and an OH here. Then the water comes out. The key thing here to know is not which H and which OH to remove. the key thing here to understand is in order to join them together, I need to remove an H and an OH so that a water comes out. Okay, can you tell me what the name of this process is again? What is it called when you do this, when you connect them together? Exactly. Okay, this is called dehydration synthesis. Right. All right, let's try this again. We're trying to build all these things over here. These things we call disaccharide. Disaccharide. Do you remember? Each one of them must have at least one of what? That's right. So you see this on a test or something, like don't even think too much. Just put down glucose, glucose, glucose. Then you have to think about what the partner is, right? Lactose is easy to remember because for lactose, it is going to be glucose plus galactose. That's right. Galactose. Kitchen sugar, sucrose, is going to be glucose plus fructose. Okay, and finally, maltose is just glucose, glucose. And I would like to remind you that these are monosaccharide. Right? Okay, very quickly. Starch. Where do we find starch? Is it in animals or plants? Plants, right? Which part of the plants? Stem and root. There you go. Stem and root of plants. Storage form of energy in plants. How about glycogen? Where do we find glycogen in our body? Liver and muscle. Do you guys know where your liver is, by the way? Can you show me your liver? Just wondering. How many livers do you have? One. Okay, good. We know that much. Which side is it on? Is it on the right or is it on the left? Right here, okay? Under your diaphragm, okay? So this is stored in liver plus muscle of animals. And that would be storage form of energy in animals. Okay, not all animals, but you know, like mammals, for example. Cellulose. Cellulose are found in plant fibers and cell wall, right? We do not have cellulose in our body. Okay, we just eat them for a good digestive, good bowel movement. Okay. What's the function of cellulose? For things that do have it, structural support. And the last one, chitin. Chitin. Where do we find it?
The shells.
The
of
sh
seafood, like,
That's right.
Yeah.
So we say exoskeleton of insects and shellfish, right? We can say shellfish, crabs, lobster, mussels, all the expensive stuff. And the main biological function is protection, right? plus structural support. And that's it. Okay, so for those of you who joined us a little bit later today, I am postponing the quiz. Okay? The quiz is not going to be on the 18th, it's going to be on the 23rd instead. Please check the news item on eCentennial later today. I will be posting information about the quiz as well as a review video. All right, thank you very much. I will see you all next week.
See the